One thing that we haven't mentioned at all yet in Rn is the length and angle between vectors. It turns out in general to figure out the length and angle in vectors for any vector space, you need something called an inner product. But in Rn, an inner product takes a particularly nice form, which is called the dot product. So the dot product of two vectors is just defined, so it's written this way, v dot w, and it's just defined to be v transpose times w. And this multiplication here is just the regular matrix product. Now, since v and w are both in Rn, the number of columns in v transpose is equal to the number of rows in w, right, as you see here. And this matrix product just produces a 1-by-1 matrix, in other words, a scalar. So you just get this combination of the entries of v and w. Now, it turns out that other than just having a really nice formula, this inner product, or this dot product in Rn, has several nice algebraic properties. So it's commutative, as you can tell just by looking at it. If you switch all the v's and w's, it gives you the same thing. It's associative with the scalar product. If you do the scalar product after you take a dot product, it's the same as doing the scalar product with one of the factors before doing the dot product. And you know, having this scalar here is just like having a bunch of a's there, so it doesn't matter whether you do multiply by a afterwards or multiply one of the two coordinates of the vectors, or one of the two collections of coordinates before the dot product, right? You're going to get the same thing. Also, it turns out that the dot product is bilinear, so this is pretty key. Bilinear just means that if you hold one factor constant and the other factor in the dot product is a linear combination, then this is a linear transformation. So you can distribute the dot product and also pull constants outside, right? And that, because the dot product is commutative, having that be the case for one factor is the same as having it the case for the other factor. And then finally, the reason that we can use this dot product to compute lengths is because if you look at v dot v, what you get is the square of the length of v, right? If you just imagine that both of these are v, you get v transpose v, and that's v1 times v1 plus v2 plus times v2 all the way up to vn times vn. And so this is v1 squared plus dot 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 plus vn squared. And just by the Pythagorean theorem in n dimensions, this is the length of the square of the length of v. So like this. These double bars are length in Rn, so the length of a vector, the square. So if you take the square root on both sides, then you get that the length of a vector, or also called the magnitude of a vector, is just the, so the, I should have written it here, the magnitude of the vector is the square root of the vector dotted with itself. The other nice thing that you can do with the dot product in Rn is you can use it to get at the angle between vectors. So it turns out that for any two vectors in Rn, v dot w happens to be the length of v times the length of w times the cosine of the angle between them. Now this isn't an obvious fact. This takes some proving, but I'm not going to prove it here. Probably you've seen this fact before in a Calc 3 class, and you may have seen it proven then. And if you haven't, you can definitely look up a proof in a calculus textbook. A nice result of this fact about if we want to know the angle between vectors, we can use this fact to calculate the angle between the vectors, because if we have these two vectors, we can definitely calculate their lengths, and then we can solve for cosine theta and then take inverse cosine to find the angle between the vectors. That's a really nice thing about the dot product, because you know, in n dimensions, it's kind of hard to know, it's hard to visualize how you would find the angle between two vectors. There's just, you know, it's so hard to, even in 3 dimensions, it's kind of hard to figure out geometrically how you would find that angle, but the dot product gives us a really straightforward algebraic way of finding it. Okay, one consequence of this nice geometric fact is that two vectors are orthogonal, that's just a fancy word for perpendicular, two vectors are orthogonal if and only if their dot product is 0. You can see that if these vectors are perpendicular, the angle between them is a right angle, and cosine of that is going to be 0, so the dot product is 0. But also, if their dot product is 0, then one of three things has to be the case. Either the magnitude of v is 0, right? So if we're imagining that this dot product is 0, either the magnitude of v has to be 0, in which case v is 0, and in that case, you know, the 0 vector sort of counts as perpendicular to everything. It also counts as parallel to everything, which is why the 0 vector is weird. It's the only vector that's parallel and perpendicular to everything. Okay, so if the dot product is 0, either v is 0, in which case these vectors count as perpendicular, w is 0, in which case these vectors count as perpendicular, or cosine theta is 0, in which case the angle between them is a right angle, in which case they're perpendicular. So what this gives us is a really nice, straightforward way to check if vectors are perpendicular. You just calculate their dot product, and the dot product is super easy to calculate, right? It's just this formula up here. So let's use the dot product for a couple things. So got my indexing all messed up. There we go. So for these two vectors, let's find the magnitude of v. So remember, the magnitude of v is just the square root of v dot v. So this is the square root of v transpose times v. And there's really no reason to write out this matrix product. There's really no reason to actually write down what v transpose is. The formula for the dot product is so easy you can usually just write it out in your head. So 3 squared is 9, 1 squared is 1, 4 squared is 16. So it looks like we're going to get the square root of 26, which is not a particularly nice number, but that's what we get. Okay, let's find the angle between v and w. Well, remember, the angle shows up in the dot product in this way. So the dot product is magnitude of v times magnitude of w times the cosine of the angle between them. So this means that the cosine of the angle between them is v dot w over magnitude of v times magnitude of w. We already know the magnitude of v. Let's find the magnitude of w. It's the square root of, let's see, 4 plus 1. So that one is nice. That comes out to be 3. Okay. So in our denominator, we get the magnitude of w is 3. The magnitude of v is the square root of 26. And then v dot w, right, that's 3 times negative 2 is minus 6. Plus 1 times 2, that's plus 2. And then plus 4 times negative 1, that's minus 4. So it looks like we're going to get negative 8 over 3 root 26. And then, you know, if you want to, you can rationalize this. Maybe that would be a nice thing to do. But we're going to get a decimal approximation when we take inverse cosine anyway, so I guess no point in rationalizing. So to get our angle, we need to take inverse cosine of negative 8 over 3 root 26. And so let's get a decimal approximation. And my calculator happens to be in degree mode, so we'll get our angle in degrees. So negative 8 divided by 3 times square root 26. Careful to get all my parentheses in the right places. And then take inverse cosine of that. And we get 121.5 degrees. Notice that this is an angle that's greater than 90 degrees. And the reason that that happened, so right, we have an angle bigger than 90 degrees, so something like this. So what is it about this value that made this angle come out to be bigger than 90 degrees? Well, these magnitudes in the denominator are always going to be greater than or equal to 0. And as long as neither of the vectors is 0, then they won't actually be 0, so they'll be positive. Okay, so this denominator is always going to be positive. So the sign of this whole thing will depend on the sign of the dot product. So if v dot w is greater than 0, then we have a positive cosine, but a positive cosine means that the angle is between 0 and pi over 2, or not equal to pi over 2 actually. Okay, and if this dot product is negative, that means that cosine of theta is negative, but that happens when theta is between pi over 2 and pi. Okay? Of course, if v dot w is exactly equal to 0, then that means that theta is exactly pi over 2, so we have a right angle. In fact, all of these go the same way. So you see, even just looking at the sign of the dot product tells you whether the vectors point generally in the same direction, generally in opposite directions, or exactly perpendicular. So the dot product is a really powerful tool for figuring out geometry in high-dimensional Rn, where we're completely unable to visualize what's going on because there are just too many dimensions. Let's look at one more example of using the dot product. So suppose we have a vector in Rn, a vector v, and we want to find the equation of the subspace through the origin that's perpendicular to v. So when I say the equation of the subspace, if you imagine in R3, if we have a single vector, what sort of subspace is going to be perpendicular to that? Well, it's going to be a plane, right? So in higher dimensions, it won't be a plane, it'll be some sort of hyperplane, I guess would be the name for it. But it's always going to be a subspace, right? So when I say the equation, we've seen in the past that a single equation, a single linear equation in n variables will slice out a plane in Rn. So we're looking for the equation for this plane, or hyperplane if we're in a higher dimensional space. All right, so if we're at the origin and we have this fixed vector v, what we need to do is come up with some equation that will be true only when we have a vector w that is in this space that's perpendicular to w. Well, we can check. So first of all, since we're trying to write an equation, we should have some variables. So w will be a vector full of variables. So x1, say, I want to use x's rather than w, so why don't I actually call this x? Just because when we write equations in Rn, we're used to using x's for our variables. So x1 through xn. V, let's say that that's v1 through vn. And everything looks like a variable here, but the thing to keep in mind is that v is actually a fixed vector. So in a particular example, these v's would be actual numbers, but these x's are going to stay variables. All right, so what we need to do is write down an equation that is true only when x is perpendicular to v, right? Because that will mean x is in this subspace that's perpendicular to v. But x perpendicular to v, right, this symbol means perpendicular, x is perpendicular to v exactly when x is, the dot product of x with v is 0. Right? So we can just write out this equation. And this equation says v1x1 plus v2x2 all the way up to vnxn is equal to 0. So you can see to write the equation of a hyperplane perpendicular to a given vector, all we have to do is throw the entries of the vector into this equation, and we get the equation that slices out this hyperspace. All right, well that's if we, right, something that was sort of implicitly assumed in this whole setup is that the origin of our coordinate system is in this subspace, right? That has to be the case if we have a subspace, because a subspace has to contain the 0 vector. But what if we want a hyperplane that is perpendicular to v but doesn't necessarily contain the origin? So what if we want, I shouldn't call it a subspace, hyperplane I guess is the term. what if we want to find the equation of a hyperplane through the point at the end of the vector w and perpendicular to the vector v? So if we have a vector v like this and a vector w like this, right? The origin is here. The end of the vector w is over here. And as a point, the coordinates of this point are the same as the coordinates of w. So, often people will conflate this point with the vector w since they have the same coordinates. In this case, where w is a vector starting at the origin and ending at a certain point, we say that w is the position vector for the point. Okay, so if we want, so what we're looking for is, let me change my picture for v so it doesn't look like it's perpendicular to w. There we go. So we want an equation for the plane through this point where w is ending and perpendicular to v. So v goes like this, and so our plane should be like this, right? All right. And what we want to be able to do is write an equation that is true exactly when a vector ends on this plane. So here's some other vector. Right? Let's call this x. How can we tell if x is ending at a place perpendicular to v? Right, here's v. Well, we need to check if something is perpendicular to v, but it's not x itself. You can see in this picture, even though x is pointing to a point on the plane that we want, x itself is not perpendicular to v. So what we need to check is perpendicular to v is this vector here. Right? That's the vector that should be perpendicular to v if we're on this hyperplane. And you can see that this green vector here is actually just x minus w. We can tell it's x minus w because if you add w to it, if you add w to this green vector, you get x. So the green vector must be x minus w. So we want to know if x minus w is perpendicular to v. So we can just dot that with 0 and set it equal to 0. Or sorry, dot that with v and set that equal to 0. So this is the equation for the plane perpendicular to v that goes through the end of w. Okay. Now if x is, if x is a vector of x's whose entries are x's, and v is a vector whose entries are just vi, and w is a vector whose entries are wi, then usually how people do this is they'll rearrange this equation distributing this dot product. So remember, the dot product distributes. So this would give us v dot x minus v dot w. And actually here I've also used the commutativity of the dot product, right? This first term should be x dot v, but the dot product is commutative, so I just turned it around because I felt like it. And then usually people move this second term to the other side, so you get v dot x equals v dot w. And then you can write everything in terms of entries if you want to write everything in terms of entries. So that would give us v1 x1 plus dot 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 plus vn xn equals v dot w. And then so usually if you're writing an equation for this hyperplane, you want to write out the terms involving the variables. So we'll write out this dot product on the left. Whether you write out this dot product on the right or not is sort of up to you, because in any particular example, v and w will both be vectors with actual numbers, like not a vector of variables. So you can actually compute this dot product and then just put whatever the result of this dot product is, just stick that on the right hand side here. So you can see, comparing this equation for an arbitrary hyperspace, or for an arbitrary hyperplane, to the equation for a hyperplane through the origin, they're almost the same. The only difference is what's on the right hand side, right? If your plane contains the origin, the right hand side has to be 0. If it doesn't contain the origin, then this dot product is going to be non-zero, and that sort of offsets the plane away from the origin, essentially.